I think we're going to be able to finish chapter 17. Again, it's short chapter. It has two things, the buffers, which we already did, and then something called titration, which I'm going to show you today. This is kind of a titration setup. What you do is you have down here, you have hydrochloric acid of an unknown concentration. In this burette, that's what they're called, not like the ones you put in your hair, but you will have your base. In this case, it's sodium hydroxide, and you'll know the concentration, okay? You're going to know your volume of your hydrochloric acid. Let's say you're going to start with 100 milliliters. So you put that in there, but you don't know the concentration of your hydrochloric acid. Then what you do is you slowly add the NaOH, and that's what a burette does. They're very calibrated. They're crazy because they're really expensive. I think one of these is like $50. I don't know why. But anyway, it allows it to go in there little by little. And they have a stirrer in here too. And they're measuring the pH. And then when the pH gets to 7, they quit. They measure how much sodium hydroxide you have of known concentration, how much acid, you knew that. So because you know the amount, and you know the amount and the concentration, with a titration, you can actually calculate the molarity of this HCl, this hydrochloric acid. Another way besides the pH probe of doing this is to put an indicator in here. And maybe some of you guys have done this before. You'll have a solution, it'll be pink. And then you'll add this stuff to it, and then all of a sudden the pink will disappear. Then you know you've neutralized it. And then again, you measure how much you use and you can calculate. That's a titration. And really what a titration is taking an acid and adding it to a base, or a base and adding it to an acid, and you're neutralizing it. And what you end up with is a salt and water. So you can take the most concentrated, nasty acids and add bases to them, and you can end up with salt and water. And then it's neutral, and you can, put it down the drain. But you can't do that when it's in this form. So first you have to neutralize it. And that's called a titration. Okay, so titration is a technique where you take either an acid or a base, and you know one of them, you're going to know the concentration of one of them. You slowly add it to the other one. Now, don't take an acid and add it to an acid, or a base and add it to a base. That's not going to work. I've seen people do it before, you guys. I'm not making it up. But if you take an acid and add it to a base, or a base and add it to an acid, you can figure out, first of all, their concentration. And when they reach that point when they're equal amounts, that's called the equivalency point. So that's what you're looking for. Okay. When the pH meter reads 7, then you know you're at your equivalency point. The acid and the base concentrations, they're not necessarily equal to each other, because stoichiometry, they might be different, but they're equivalent to each other. In other words, the amounts of each equal each other. So now your solution is neutral. Okay. A titration of a strong acid and a strong base is the easiest one to do. Here is if you graphed it for your pH. Okay, what will happen here, you start out with your acid, and this is your amounts that you're adding, and you notice it just slowly goes up, and then all of a sudden, whoop, it goes way up. And then it'll become base. So your equivalency point is right at 7, and then you'd read this, and this is how much you needed to add. Okay, so equivalency point is going to be 7. That's when they equal each other. Okay, and when you do a strong acid and a strong base, it makes a really nice graph like this. Now, if you have a strong base and a weak acid, you've got some buffer things going on. You're going to have some other issues, so it's not going to be as pretty. Okay, so just before and after the equivalency point, the pH, you can see it rises crazy much. From here to here, it goes from about 3 to 11 within, so this is your equivalency point. If you're mapping this out, you'd add, and you'd swivel, and it wouldn't change, and it wouldn't change, and it wouldn't change, and all of a sudden, woof, it changes a bunch. Okay, and that's what happens when you do a strong acid and a strong base. Okay, and again, your equivalency points, you want the pH to be 7, because that's when it's neutral. Okay, as you add more base now, the pH again is going to level off, because now it's mostly base. You've used up your acid. They've neutralized all they can. They're done, and now you're just adding base. Okay, a titration with a strong base and a strong acid, the curve is just going to be the opposite, because you're going to start at a high pH, and you're adding acid to it, so now it's going to go down. Okay, and again, the equivalency point is still going to be at 7, because that's when things are neutral. But here you're going to start at a high number, because base's pH is high, and acid's pH is low. So you get the same shape of a curve, just in reverse order when you start with a base. Okay, so a strong base and a strong acid, it's just flipped. Okay, but you're looking for the same thing. You're looking for the equivalency point at 7. And like I said, you'll add stuff and it won't much will happen, and you'll get bored and you'll stop paying attention, and pretty soon, whoop, it goes way down. And you can see it happens really quick here. Okay, this point at here, this is the volume you would say you need to add to neutralize it, 50 milliliters in this case. Okay, so again, when you do the reverse of a strong base with a strong acid, your pH is going to be high. When you do a strong acid with a strong base, your pH is going to be low. It just depends on which one you start with. Okay, now a lot of times when you do a titration, you can use an indicator. And we talked about indicators a little bit. Indicators are weak acids, and they change colors. They have different colors in their conjugate base forms. Some of them are like one color in an acid, one color in a base. They're not as useful simply because, is it a strong acid? Is it a strong base? I mean, you know, it's just one color here, one color there. And if it's neutral, you know, it won't give you a color. But a common one to use in titration is called phenolphthalein. It's pink. It's the stuff they use if you watch the CSI shows, you know, where they wipe it to see if it's blood and they put the little thing on it. Well, that's phenolphthalein with a little bit of hydrogen peroxide. And it reacts, because blood is basic, so it reacts to that and turns pink. And then you know, oh, it's human blood. Okay? That's actually got a special name for it. I can't remember. It's been a while since I taught forensics. But anyway, you can see, here's phenolphthalein. Okay? Phenolphthalein is, what'll happen if you do a titration with a phenolphthalein, you'll have to start with a base. You put up a couple drops in it, swirl it around, and it turns bright pink. It's really pretty pink. Okay? So then you add the acid, you swirl and you swirl and you swirl, and pretty soon it totally disappears. It's clear. Now you've reached equivalency point. Now it's equal. The problem is if you keep adding acid to it, it's going to go lower and lower and lower, and now you might have an acidic solution, but you can't tell that because phenolphthalein only tells you if you have a base. It's pink in the presence of a base, and you can see it here. You know, and this isn't the pretty, it's way prettier than this. This is kind of purplish. Phenolphthalein is really kind of a cool pink. Okay, here's some other ones, methyl orange. Another one that they use is bromothymol blue. Bromothymol blue is a little bit different because it's yellow in an acid. It's green when it's neutral, and it's blue when it's a base. But again, it's not really a conjugate base. So, but anyway, each indicator has its own pH range, which changes colors. So which one you want to use depends on what you're looking for. Are you starting with a base? Are you starting with an acid? Is it a strong base? You know, the most common is honestly phenolphthalein. I think phenolphthalein is kind of cheap, and it's really cool when it changes colors. But again, which one you use just depends. A lot of people don't even use them anymore. They just use the pH probes, because when the pH probe gets to 7, you're exactly at neutral. So again, it just depends on which one you want to use. Okay, indicator choice can be critical. Again, here's your phenolphthalein. It's going to change at, you know, it doesn't even change at 7. It changes at 8.3. Here's methyl red. So again, whatever indicator you're going to use depends on what you're starting with, what you're ending with, what you're looking for. Okay. Okay, so how to solve a titration problem? Where are we at? Oh, we got lots of time. Good. All right, there are 4 steps. Now, this is not doing the actual titration. This is, you've got the information from your titration and you want to solve it. You want to find your concentration of what your unknown acid or base. Okay, so the first thing you do, because you're going to know 3 things. One of either your acid or base, you're going to know its concentrations and its volume. And then the other one, you're going to know just one thing about it. And your job is to find your unknown. So the first thing you do, you find the moles of the known solution by multiplying. The way it's going to give you the concentration, which is molarity. If you take molarity times volume, you're going to get moles. Okay. Second step is a balanced equation. For some people, this is a problem. Just remember, when you're doing a balanced equation, when you take in an acid and a base, you always end up with salt and water. And by salt, it does not have to be NaCl. It could be whatever metal you have there, and whatever, take away the H and the OH and put whatever you have left, and that's your part of your equation. Then you do a mole ratio. Okay, stoichiometry. You're going to take, because you already found the moles of your known solution, use that to find your moles of your unknown. Where's the mole ratio going to come from? Your balanced equation. And then you'll have your moles of your unknown. You'll know its volume. You can find its concentration. Okay, So this is all stuff you've done. It just kind of is putting it all together. All right, so here's my example. Find the unknown. We have an unknown molarity of 250 milliliters of our base, NaOH. How do I know it's base? OH, you guys. If it's titrated with 410 milliliters of 1.6 molar HCl. So I'm going to start with this one first because I know two things about the acid. Okay, so I multiply them together. 1.6 times 0.41. Okay, again, I got to change this, remember, to liters. Molarity. Multiply the two, I'll get the moles of my HCl. That's step one. Okay. Step two, a balanced equation. Take your acid, hydrogen first, and your base, OH second. You're going to end up with water, so take out the H and the OH. That's water, H2O. What do you have left? NaCl. Make sure they're written properly. Sodium's +1, chlorine's -1. Yay, they're written properly. And this is also balanced. Hydrochloric acid and sodium hydroxide are a very common titration. The nice thing about them, it's a really easy equation to write. You don't have to balance it, it's already balanced. Okay, so now we're doing our 1-to-1, our mole ratio. So we take what we know, moles of HCl, put 1 mole of HCl on the bottom, and then 1 mole of NaOH on the bottom, because from our balanced equation, these are both 1s. That doesn't always happen. Sometimes we have 2s and 3s in here, you guys. But in this case, it's nice. It's going to be the same. Okay, the last step is to find the molarity of your unknown. I got moles. I got the volume. It says 250 milliliters. That's 0.25 liters. So the molarity of my NaOH, my sodium hydroxide, is going to be 2.62. Okay, so if I want to neutralize 410 milliliters of 1.6 molar HCl, I need to add 250 milliliters of 2.62 molar NaOH. That will neutralize it. Okay, so step one, multiply the two things you know and find your moles. Balanced equation, then find your moles of your unknown, and then find your molarity. Okay, you can also do that. Here's another one. Will help. Yeah, I should be okay. All right, so find the unknown concentration of aluminum hydroxide when 63 milliliters of 1.05 molar H2O is needed to titrate it. So here I know two things. So step number one, I'm going to take 1.05 times 0.037. Okay, that's how I got this. I took this times this. Okay, but again, I got to change this to milliliters. Then do your balanced equation. This is not a simple equation to balance. Okay, we got my acid, H2SO4, hydrogen's listed first. Got my base, OH. So now I take the H and the OH together and I get water. And what do I have left over? I have aluminum and I have sulfate. So I put them together. But I can't just write AlSO4. I have to balance the charges. Now you can look the charges up on your chart that you have, or you can do this. Well, let's see, hydroxide has a 3 here, so aluminum must be +3. Hydrogen has a 2 by it, so sulfate must be -2. Okay, or you can just look them up, either or, but I crisscrossed them. So once I wrote this out properly, then I put a 2 in front of aluminum, a 3 in front of the H2SO4, and now I have 6 hydrogen here and 6 here. That's 12. So by putting a 6 here, I balance my equation. So they're not always super simple to balance, you guys. This is the hardest one you'll see, is with the 2s and the 3s. Okay, so now I got my moles of H2SO4. I did that in the first part. Now I have to put moles of what I'm trying to get rid of, moles of H2SO4 on the bottom, moles of what I'm trying to find, aluminum hydroxide, my base on top. By my equation, this is a 2 and this is a 3. So I take this times 2, divide by 3, and this is my moles of aluminum hydroxide. And then I take the moles that I just found and I divide by the volume. The volume says I have 0.037 milliliters or 0.037 liters. Okay, so again, here you take what you know. I know these two things, so I took 0.063 times 1.05. That's how I got this. Then I wrote my balanced equation. Then I did my mole to mole ratio, and then I got the concentration of my unknown. Oh, I'm going to run out of time. I'm going to, I'll do one more where I add, there's one where you do volume. So there's going to be one more part of the video, but I'm going to run out of time here in a couple seconds. So we'll add this and then I'll do one more slide.